So let us start with routes have its criteria, RH criteria. Now let me tell you that RH criteria is used to find out absolute stability. Absolute stability meaning what? Meaning what? Location of poles. The poles lying on imaginary axis, poles lying on the left half, poles lying on the right half of a plane. Everything you'll get pole locations, pole location, and you can get pole values also. Okay, we shall discuss all the rules with regards to this, and then we will quickly see one example demonstrating almost all the laws discussed. Fine, so let's get started. So what we will do is we will first take the denominator of a transfer function, closed loop transfer function, that is 1 plus GSHS is equals to 0. Fine. Then what we will be doing is we will be arranging, we will be seeing for, if any s is coming out in common or what. For example, if equation is s ki power 7, s ki power 6, s ki power 5, 4 and so on, and s in the end, in that case you can take s common. Okay, s ki power 6 plus and so on 1 s, so there will be one pole at origin for sure, one pole at origin for sure, so you should not forget this also. But it's always make sure that your last term is always constant. Okay, it is not a function of s, it's always a constant. Fine, so let's get started with the rules of it. We will check for odd row which is 0. From there what we will get to know, we will get to know the the order of that will give us possibly those many roots lie on the imaginary axis. Okay, where do they lie and what is their exact value, we'll get to know much later. But what we can know is two things from odd row 0. What we'll take is, if odd row is 0, then we will take auxiliary equation which is just above the odd row. We'll differentiate it, so we'll do dk upon ds of that. We'll equate it to 0, and then we will fill the row which is 0, and then we'll proceed our calculation as it is. What we will be observing is, we'll be observing the sign changes after auxiliary equation, so that will give us what value alpha. And alpha, if there are multiple odd row 0, then we will take the highest auxiliary equation ka highest auxiliary equation power. Fine, so what number of that is nothing but useful to the alpha, and highest auxiliary equation power is used to find out number of imaginary roots. Number of imaginary root is highest power of AE, auxiliary equation, minus 2 into alpha, where alpha is number of sign changes post auxiliary equation. Okay, so that will give you the number of imaginary roots, and total number of signs throughout will give us total number of roots lying on right hand side. Okay, so with that, and so what we will be getting till now, we'll be getting the locations of root, how many are lying on imaginary axis, how many on right hand side, how many lie on left hand side, and if at all any common you have taken, then how many poles lie at origin. So you have got the location of that. But how do you get the exact value? So roots of auxiliary equation, roots of AE will give you two roots, let's say two roots. So numerator n of s upon d of s. Okay, so what you will be doing is, you will be, whatever your function is d of s, let's say their roots are AE ka roots plus some other roots also. So once you divide this two, you will get the location of other two roots also. Now what I'm trying to tell is, I'll just show you one example. Fine, so let's see. Now this is the polynomial equation. What we'll do is, you have firstly arranged all the coefficients in first two rows. Then you see that s ki power 1 row becomes 0. Okay, then you make your auxiliary equation to be minus 2s square plus 2 is equals to 0. From that you get minus 4s is equals to, basically you get minus 4s, that you substitute here in s ki power 1. So from here you get that maybe some poles lie on, some pole, since order is 0, we can say maybe some pole lie on imaginary axis. may pole on imaginary axis. Once this is found out, we move ahead and we do all calculations. Now we check. Now we see order for number of roots on imaginary axis. Firstly, we'll see highest order of auxiliary equation, that is nothing but 2 minus 2 into alpha, where alpha is number of sign changes post auxiliary equation. We see it is ones. So 2 minus 2 into 1, that comes out to be 0, which means there are 0 poles on imaginary axis. Fine. So 0 poles on imaginary axis, good enough. Then we calculate number of total sign changes. So we get once and we get twice. So 2 sign changes are there altogether. My meaning what? Number of poles on imaginary axis comes out to be 0. On RHS comes out to be 2. Total order of the equation is 4, meaning LHS poles are nothing but 2. Okay, LHS poles are 2. So this is what information we have got. Now we have got the location, but what are the exact values? To get exact values, you will find out roots of auxiliary equation. Roots of auxiliary equation are also roots of D of S. Okay, so from that you got already 2 roots, and using dividing D of S upon A of S will give you rest of the roots. Okay, this comes out to be the answer. From this, if you factorize it, you will be getting other 2 roots also. Okay, so you have got technically all 4 roots from this. Okay, so this is the concept of finding the roots and their allocation of roots and their exact values. Now let's say there are so here only one row odd row is becoming 0, but let's say here 2 odd rows were becoming 0. Let's say this row and this row. In that case, the difference would be only highest for finding imaginary poles. Okay, highest order would be 3 and alpha would be probably once and twice 2. So h minus 2 alpha would be your thing. Okay, so sorry, yes, after that is nothing but once and twice. So you would be checking that you will be considering only always the highest power if there are more than 1 rows getting 0, odd rows getting 0. Fine. So this was the concept. Now let me tell you one more concept, that if one odd row is 0, in that case system is marginally stable. Okay, marginally stable because poles come on imaginary axis. If let's say repeated odd rows are 0, and you are getting repeated roots on imaginary axis, then the system is unstable. And also roots of auxiliary equation is nothing but omega n. We can also say that roots of auxiliary equation it crosses imaginary axis. Okay, fine. So this was the concept. Now let's move to the another concept number 2, which is conditional stability. So let's say if a question they asked you stability around a point, let's say s is equals to -1. In that case, what you will do is s minus 1 is equals to s is equals to -1. Okay, so what you will do is s minus 1, s plus 1 is equals to z. So what you will be doing is s plus 1 equals to z, s is equals to z minus 1. So in place of s, you will be substituting it with z minus 1, and then you will see the location of z. Okay, now for third order equation, it becomes very simple that inner product must be greater than outer product for stable system, and for marginally stable they both are equal, inner product equal to outer product, and omega n is nothing but root b. Okay, essential concept. Okay, let's stop here. This was all about the root locus story. Sorry, this was all about the RH story. Thank you so much. Tomorrow we'll be seeing about root locus.